for doing heap stuff. And again, I made quite a large worksheet for today. As you see, it's kind of 2 full pages, but it does cover a lot of the stuff in the videos, just because I know those are long videos, and probably anything that where I talk for that long, 25 minutes, is probably worth just kind of doing in some sort of exercise or activity. So again, the main things I talked about, or when we were talking about heap implementation, was first of all, we can index this starting at index 0 or 1 in our array. And when we've got index 0, again, this is going to be index 0 of the array, 1, 2, 3, 4, 5, 6, etc., etc. We see that for any node, its left child is going to be 2 times the index plus 1, and the right child is going to be 2 times the index plus 2. And the parent is going to be I minus 1 divided by 2, and it's going to be the floor of that. So again, looking at 6 here, 6's index is 2. Its left child is, again, 2 times 2 plus 1, which is 5. And we see it is 5 here. Its right child is going to be 2 times 2 plus 2, which is 4, 6. We see it is 6 here. So again, that's how we can access items in our array. Again, we're starting with this node here. Its left child is index number 2 plus 1, which is here, and its right child is 2 times 2 plus 2. Again, looking at a node and getting its parent, like this 12 here, this 12 here is 10. We know that we do that index number 10 minus 1 divided by 2, and we get the floor of that. So it's going to be 9 over 2, which is going to be 4.5. The floor of that is 4. So we expect that this node's parent is going to be at index 4, which we see that's where the 9 is. Does that make sense? Cool. This is just how we can actually implement a heap and get this structure with an array. Because we're not actually using nodes, like we don't actually have nodes with pointers to left and right children. What we're doing is we're implementing this with an array. So all we've really got in terms of our data structure is this array here, this data, which is an array of integers. And again, given that, we can access any node. We can start at the root, which is index 0, and we can reach any node by saying, if I want to go to this node's left, we just multiply the index number times 2 plus 1. If we want to go right from there, we can go 2 times that index number plus 2. So it's just a way of thinking about how we can implement a heap using an array, where again we can still get this concept of a tree here where we've got nodes with left and right children. We're not actually using any nodes, so we don't actually have any nodes with left and right pointers. Yeah, I'm just kind of showing that this is how in this array implementation where we don't actually have a current that we can say, oh, current equals head or current equals root, and then current equals current dot left or right. It's we can traverse this structure using index numbers, and instead of like a get left, or I guess our get left method would just be return the index number of this times the current index times 2 plus 1. And I talked about how you can do this with an array starting at index 0, which we're showing here. This is zero-based indexing. But it's a little bit more complicated, especially getting the parent of a node. Again, to get the parent, you have to minus 1 of your index number and then divide it by 2. So when we scroll down a little bit, we'll see that with the one-based indexing method, it makes this formula to get a node's left and right child and parent a little bit easier. So again, our index numbers are starting, our first element is now stored at index 1. We skip index 0. And we're going to see it just makes this formula for accessing nodes a little bit easier. So in this case, it's just going to be 2 times the index number. The right child is going to be 2 times the index number plus 1. And the parent's just going to be I divided by 2, as opposed to I minus 1 divided by 2. So again, slightly slightly easier. These are the index numbers of our nodes. And again, in this implementation, we'll just start our like size variable, or where we're inserting our first item at 1 instead of 0. But again, an example here, doing the same example, if we start at 6, we know that index number is 3. So it's left. To get the left, to get 6, if we're at the node 6, we want to get its the value of its, or the index in the array of its left child. We'd again just say 2 times 3. So we should say that its left child should be found at index 6, which we see it is. 2 times 3 gets us to 6. And its right child will be at 6 plus 1, which is 7. And we see, yes, the right child is 20 and it's at index 7. Similar to get the parent, if we were trying to get the parent, I don't know, of again, this 12, we see this 12 is at index 11. So it should be 11 divided by 2, the floor of that, because we're doing integer division, which will just be 5. So we do see that 12's parent should be at index 5. 12's parent is indeed the 9 at index 5. So again, I know I erased this, but the formula is just a little bit easier if we use 1-base indexing as opposed to 0-base indexing, but it's not. But again, both of them are still constant time. We can access these really easily. I just wanted to make note of this because these numbers do change. And again, if you see code, if you see heap implementations online or in different textbooks, some of them just say, we assume that it's going to be a 1-base or a 0-base indexing. So obviously some of these values will be a little bit different. And it can be confusing why some of them have these different numbers. And it's just because, yeah, the two really common implementations are to implement a heap using an array in either of these two methods. Does that make sense? But other than that, we'll see that the code itself is going to be fairly similar in terms of how we're going to actually implement insertions and removals. Any questions? So I guess the ternary heaps, I think would just, not really. I was just trying to come up with a quiz question that would make you kind of think a little bit beyond just kind of rinsing and repeating what I'd done in the videos, just think a little bit more. I guess the main thing about, I guess, heaps, like binary, ternary, and heaps with more and more children is just because a lot of heap operations are bound by the height. Whereas again, with if we've got a binary tree, our height is log 2 of n if it's balanced, right? And that's because, well, we can store up to, I guess, 2 to the power of h minus 1 nodes with a tree at a given height. But the thing is, if we have each of our nodes are ternary nodes or any other nodes, the number of nodes we can store in a given height is like 3 to the power of h or 4 to the power of h, depending on how many children each node can have. So it just means that the height to access, if all of our operations are bound by the height, it means that we can store more nodes with us in a smaller height. So it just means that we can do slightly better log-based timed operations. But again, something that's log-based 2 of n versus log-based 3 of n versus log-based 4 of n, we still kind of classify that as a log n algorithm. But again, obviously, log-base 3 of n is faster than log-base 2 of n, and so like the higher the base we can get is the better. I guess, yeah, the issue is binary heaps are the easiest because, yeah, it's just a single comparison knowing whether to go left or right. Whereas if they've got more children, there's actually more work to determine which child to choose as you're trying to find an item in there. Yeah, so there is way less heights. And we're going to actually talk about different types of trees, which the idea is just to reduce the height as much as possible. And that's what we will see that in the tree unit. Good question though. Any other questions? Yeah, it's really it is quite simple. So again, for those of you that missed the video, really the two things that we want to the properties we want to maintain in a binary heap, and we're going to have to think about these as we do our insertions and our removals, are that we've got the heap shape property. And this is why I had those videos on tree terminology before talking about heaps. I guess it depends. I'd probably call them more of an abstract data type because there's also operations associated with them. Whereas the data structure we usually use to implement them is typically an array, but they could also be implemented with a linked list. So I'd probably consider them an abstract data type just because essentially an abstract data type is kind of the data in combination with the operations on that data. So again, we know that the data that we store in a heap is going to be something with these keys that determine priority, and the operations that we're going to be able to insert and remove the min or max based on whether it's a min or max heap. So the heap shape property is just going to be that we want it to be a complete binary tree in our case, but we did see it can be other types of trees as well. But and either way, we always want it to be complete. And again, just for those of you that might be behind in the videos, what that means is that all levels are going to be filled in the tree down to the last level, and the last level is going to be filled with everything on the leftmost side. So again, any levels that aren't filled will only be missing nodes on the very right side. So it's going to be a balanced tree. It could even be a perfect tree. But if any nodes are missing from a perfect tree, they're going to be missing on the bottom level on the very rightmost side. The heap order property is that, again, because we're doing min heap here, I'm going to say that all nodes except for the root have a key, I guess in this case, the keys are going to be greater than or equal to the key of their parent. So as we see, again, 5 is greater than or equal to 4, its parent, 15 is greater than or equal to 5, 9 is greater than or equal to 5, 16 is greater than or equal to 15, 25 is greater than or equal to 15. Again, every node in this tree has a key value greater than or equal to its parent. Any questions about this, about either of these two properties? And again, as I talked about in the video, again, this is strictly a parent-child relationship. Again, that it doesn't mean that one key is going to be bigger than the other. As we see here, in one case, the 15 is bigger than 9, in the other case, 7 is bigger than 20. It doesn't mean that keys on a certain level are going to be higher than other keys. Again, we've got a 20 up here and just an 11 down here and a 12 down here. So we've got some 2-digit numbers up here and some, I guess we don't have 1-digit numbers, but some larger 2-digit numbers up here than some of the numbers on the third level. The only thing that has to remain true is that every node has to have this order property with its parent. So again, if we look at all of these arrows, those are just the parent-child relationship has to be maintained. And again, that's going to be different whether it's a min or a max heap. So every parent node will be higher priority, but lower value in a min heap. So a min heap means the minimum value is kind of at the top, whereas a max heap would have the highest number up here. So this would have to be the highest number. It depends if it's a min or max heap. So in this case, a min heap means that the highest priority item is the smallest number. So in a min heap, the minimum value is actually the highest priority, so that would be the one we want to remove first. In a max heap, the element with the largest valued key would be the item we'd want to remove first. Does that make sense? Any other questions? So this would be opposite for a max heap. In a max heap, all nodes would have to have a less than or equal key than their parent. So that's why I circled this before I determined what to use there. And maybe that clarifies things a bit. Any questions about this? Okay. I might clear this so I can scroll down, because I think what I'll do is I want to kind of do this visualization of what happens with the insert together with the actual code below. So I might clear this and scroll down if that's okay. I'm not sure if people are still copying stuff down. Looks maybe okay. Okay. This is probably a good spot here. Okay. So let's say that we want to insert a 4 into this heap. So again, what that means is that we're going to put a 4 into the first open spot of the array. And what we'll see is that also equates to this position here. Oh, darn. I think I changed something in the, I didn't save it. But so again, so we've maintained the shape. Again, it's still a complete binary tree. Again, the only 2 nodes missing from the bottom level are over here, and they're on the rightmost side, which is great. But now the heap order property is what we need to think about next. So again, we need to make sure that every node has a key that's greater than its parent and greater than or equal to its parent, and 4 is not greater than or equal to 7. So we need to make this comparison. We'll see, oh, I need to swap these. So what we kind of want to do here is we want to effectively swap these so we get the seven down here and the 4 up here. Yeah, that's a bad color. So again, what we're going to do is we're going to say, okay, I want to compare myself with my parent, and we know that index is going to be I divided by 2. So we're going to kind of say, okay, is this node ordered well with its parent. No, it's not, so I'm going to swap them. So I'm essentially swapping a 7 to here and putting the 4 here now. So yeah, we've effectively done a little swap here. And now again, we're going to ask that same question. Do I need to swap it with its parent? Is 4 less than 6? No, it's not. So I want to swap this again. And I want to put, I guess, I'm going to actually have the 6 here and move the 4 up even further. So I'm again going to say, okay, now I'm still out of order. So I'm going to make this swap occur as well. So the 4 is going to go here. The 6 is going to be here, and the 7 is going to be at the end. And then I can again ask that same question. Do I need to swap with my parent? No, I don't. So this will be our final, what the array looks like at the end. So again, if I erase all this stuff I've done here, really what we did is we first tried to insert a 4. And then we noticed we had to actually bubble it up twice. We needed to bubble it up to here. We needed to bubble it up to there. And then when we got there, we realized everything was in order. So what this right side of the tree looks like I don't have enough space here. So what this whole tree looks, I'll read on the right side. So all we've done on the right side is we've had a 4 here originally. It used to point to a 6, but now we've got a 4 to its right. The 4's right child is still the same node here, 20. Its left child is now the 6. The 6's left child is the 11, but its right child is the 7. And this is all the same. But we swapped the 7 and we swapped the 7 down to here, the 6 down to here, and we put the 4 as the root's right child. I'm not sure you're asking, Demandeep, about popping and putting elements to the right. Yeah, like I have space right here, which is these 2 spots. Pop the largest and put it there. But we don't know where the largest value is. Well, the thing is again, we don't know how many times we'd have to do that. With what we've done here is we've had to do, we'll at most ever have to swap it all the way. We'll at most have to bubble it up to the top in the worst case. Which isn't going to be, again, if it's bound by log n, that means this insertion is not going to be that expensive. We see here we had to move the 4 almost to the top. And again, it was only 2 swaps. And that's gonna be way faster than trying to search through this array and restructure it. We're just doing 2 swaps as opposed to, which is probably a lot cheaper than various other ways of trying to make sure this is sorted. Because we know that all this is already in order. So we don't actually need to change anything outside of this particular area. So we've inserted to the left of 7. So the only place our heap order property might be violated is right here. Because we know that this is already, if it's already a valid heap, we know that everything over here is already has the heap order property correct. So the only one that could be violated is where we just inserted our new node right here. So that's the only place we need to check if the order property is violated. And then when we swap it, we need to continue just checking until I've swapped it up enough places where that order property is restored. So we only ever need to check it where we actually make that insertion. For min heaps, yeah, for min heaps, you won't actually know where the max value is. And that's why, again, typically heaps are either min heaps or max heaps, because there's no ordering within the heap. It's just, they're ordered just so you can continue to get the min value or continue to get the max value. So yeah, it would be a costly operation to find the max value. It will be O of n, Jacob. So now that we've kind of mapped what this looks like here, let's actually try and look at the code. So again, I've got an insert method, and I'm not sure if those of you have done generics I know in 115 you covered generics, but I'm saying that the type is actually type T. And that just means that with generics in Java, that allows you to say that this could be any type of heap. It could be holding integers, it could be holding strings, it could be holding some other object. But whatever it is, we're just going to say that we're just going to assume that whatever this object type is, we know how to compare the different keys and order one key above another one. In this particular example, obviously this T is just an int. But this is the same for any type of object that we're creating a heap to store. The only thing is we need to know how to compare these object types, one against another. So size is keeping track of how many elements are in the underlying array, and the capacity is just probably the length of the array, how many elements the array can actually hold. So again, I'm saying that if we're already at capacity, we can't actually insert a new item. So we'll throw some exception and post some error message, and that's it. But we're not going to focus on that too much right now. But otherwise, what we're going to do is, I guess we'd probably assume that right now our size variable is probably initially saying that the size is right here. Size is keeping track of the number of elements. So we're saying move size up 1, and then put the new key in that. So move size up to here, and then put the new element, the 4, in that place. So we've put this new key, this 4, into the array at that particular spot. And now we're just going to do this bubble up, which says, okay, now I'm going to check to make sure that the order property is restored. So then we're just calling this bubble up, and its goal is to restore the heap property. So what do we think we're passing this bubble up method? What is the thing we're giving it as a parameter? We are giving it size, but what I'm going to do is I'm actually going to call it the index, because we're giving it the index of a node, and this is a recursive method. So we're giving it the index of the 4 to bubble up, but then we're going to call this recursively. Oh, sorry, this should be bubble up. This should be bubble up. We're going to call this recursively, again, to see if we need to continue bubbling it up like we did multiple times. Let me get my spotlight out. Like we did multiple times I don't know how the spotlight works, it turns out. Like we did multiple times up here. We did ended up bubbling it up multiple times. So what I'll say is we'll give it the index. And then I've got an if statement before I actually do the bubble. And what do you think I want to do in this first if statement? Yeah, so now we've already know it's not full because we would have actually thrown an error out here. But now all we're worried about is making sure that the order property is returned. Before we compare it with its parent, what do we need to do? I think what James said is what I was looking for here. We actually want to make sure its parent exists. So how do we know if it even has a parent? What should we ask about this index? So we can say if I divided by 2 is not equal to null, but again, we're really just all we are is an index number. We're just an integer value. So asking if an integer divided by 2 is not equal to null, I mean, if the number again, if we're at index 0 and 0 divided by 2 is still 0. So I think, again, if we look at our indexes up here, 0, 1, 2, 3, what's the first index that actually has a parent? Yeah, so it's 2. So I think as long as our index is greater than 1, then we know we've got a parent. Because that means we're at index 2 or beyond up here. So we're somewhere down in this array, which is great. And if we're index 1, that means we're the root. Obviously, this is dependent. This is assuming we're doing one-based indexing, which we are in this particular implementation. So as long as index is greater than 1, then we know we have a parent. So now we can actually just compare the value with the parent to see if we need to do this swap. So if the data, if my value is less than my parent's value, which is index divided by 2, then we know that we're going to swap here. So we kind of said if 4's value is less than 7, then we're going to swap 4 and 7 in the array, which is what we did here. And now we're down to this. Now we've got our array looking like this, where we've swapped the 4 and the 7 here. But now when we call this recursively, what do we want to do? What's the next index when we call this function again? What's the next index we want to be looking at? Yeah, so it's going to be index divided by 2. So we compared this index with the 7, and then we said, now let's call this method again, but the index number we're going to be at is this index. We're going to compare that with its parent, which is going to be index divided by 2. And we're just going to say, is that index at least 1? Does it have a parent? And if it's out of order with its parent, then swap and continue calling the recursion. If we ever find that it's not out of order, we're just going to break out of the method. If we ever find that we're already at the top, we're already at the root of the tree, we're just going to break out of the method. So all this method does is it keeps swapping while there's these until the order property is maintained, which occurs when the two nodes are in order, or we bubble it all the way up to the top, so it's now the root. The base case, I mean, I guess we could say if we could have rewritten this differently, the base case could have just been if index is less than or equal to 1, then return. Otherwise, we're going to keep bubbling. I had it kind of the opposite. I just said as long as it's greater than 1, we're going to go into this recursive call. But essentially, the base case here, we would do nothing. We'd stop our recursion if the index is less than 1. I guess, or we could say, you could also, I guess, say if index is less than or equal to 1, or data index is greater than or equal to data we return. That's our base case. Otherwise, do the recursion. So you can structure the if statements differently to have it so there's actually like a base case, then a recursive call. But how this is structured is just kind of saying if these things, we've kind of got our base case set up here. If these things aren't true, then we're going to do the recursive call. Otherwise, we can stop doing this recursion. Does that make sense, Leo? Yeah. So you can yeah. For methods that don't actually return anything, the base case is kind of just making sure you don't do the recursive call. But I could have set up with a base case and just said return from this method right now. Good question. Any other questions? Okay, so the last thing I want to talk about, I wasn't sure how far we get today. I guess we can just try to complete page 1 and we can go to removal next day. But so the last thing we want to talk about was the running time of insert down here. So again, what we've already kind of talked about this, but what we see is the number of times the recursion is going to call is, again, we think about this, it's always going to be like T of n is going to be, we're calling the recursion with this index number divided by 2, and then there's a number of comparisons we're doing as well, some plus some small number of comparisons. So plus some small constant, I don't know, a. But as we see, we've got this T of n over 2, which means that in terms of the number of times we're going to do this, it's going to be n, then n over 2, then n over 4, then n over, so it's going to be n over 2 to the I, which we're going to see is bound by log n. So and we already saw this visually, how the maximum number of times we can actually bubble something up is based on the height of a balanced tree. And we know the height of a balanced tree is bound by log n. So as Jacob's saying, this is bound by log n. And I mean, if we insert a high value, it might actually require no swaps at all. So again, that's a strict upper bound. Whereas again, depending on how we insert things, that's just the worst case. If we happen to swap, if we happen to be inserting items that are in the reverse order, which if you think about that as with something like bubble sort or insertion sort or even quick sort, if you've got something in the reverse order, the runtime is n squared. It's quite bad. Whereas here our insert is, even in the worst case, it's just going to be doing log n for each insert. So in other cases it can be much closer to constant. So this is quite a good overall runtime, and independent of how badly the the input data might be with respect to worst case. Does that make sense? So I guess, yeah, it is already 10:20. I guess this is an okay time to wrap up, and we can move to the second half, and we'll kind of talk about why we're even doing this and how this relates to some of our other sorting. Because again, what we're going to see is this insert and removal can be used together as this way of doing a priority queue sort. So we'll talk about removal, then we'll wrap things up by talking about how these together create a sorting algorithm, and then talk about why we might do this over some of the other sorting algorithms we've talked about previously. So I can wrap it up there for today. I have office hours in a few hours, but I can still stick around for a few minutes to answer any questions you might have.
The recording has stopped.
If not, maybe see you at office hours today, or see you on Friday. Good luck finishing off the assignment. No problem. Thanks, Logan, Ethan, Jackson, Camilla. I can check Sabrina. Thanks, Jen Hong. Yeah, you can import arrays, Jonathan. Thanks, Samantha. See ya. Shanielle, my actual implementation code doesn't look terribly different than what I actually have in the description. Again, I first check if the two arrays are equal. Otherwise, I break them up, and then I say, oh, do these two match, or these two match, or these two match, or these two match? So I just I do a lot of recursion calls, and I let the recursion do most of the work. The only time you're ever having to look, the only method you really need to write that compares arrays is a method that just says, are these two arrays equal? Sabrina. Doesn't look like it did submit, Sabrina. I thought that usually it warns you and says you need to submit now. But it doesn't look like there's a submission. Oh, really? Because usually, so students get one chance to submit after the due date if they haven't already submitted. Like I thought this usually pops up and says, oh, you need to submit right now or something. Huh, weird. Yeah, I can see you started, but and there's people that started after you. Yeah, I thought it updated and said like, oh, you need to submit now or not. But again, yeah, I can't actually see this as a student. It allows me to preview the exams, but it never like shows me what happens when the time limit occurs. Have you done most of the other ones? Okay, yeah, looks like, cool. Yeah, we'll see. At the end of the term, I can take a look. I know that there has been some issues with some of them, so I might be able to like drop the lowest score.